Good afternoon, everyone.
Good afternoon.
Good afternoon.
How are you?
Good. How are you doing, Professor?
Good, good. Thank you. Bilgin is here. Bilgin. Dash. Christian. Joseph. Okay. As I mentioned last time, we will have midterm exam next week. Next Tuesday, July 8th. And the midterm will cover from the beginning up to the end of notes 6. So today is not included in the midterm, but of course will be included later, okay? In last time we spoke about important point about don't care midterm. So when we mentioned when we fill out the Karnaugh map, don't care function is given also, and if we have if we are given don't care function, so the main terms related to the don't care means inside this box we put x. Inside this box we put x. Let me show you again what we mentioned to just remember. Yeah. So as we mentioned, like in this example here, we have the function f is the sum of these midterms. Everyone sees a slide?
Yes.
I see it.
Okay, good. So like f equals sum or sigma 1 and 3. So this means m1 inside the box, m1, or the midterm m1 is 1, m3 is 1, m7 is 1, and so on, which has the don't care conditions D, which is sigma 0 and 2 and 5. So means M0 is don't care, which we put X here. M2 don't care. M5 don't care. Don't care means it doesn't matter if you consider it 0 or 1. It doesn't affect on the function. So 0 or 1, it doesn't affect on the function. But the advantage of using these don't care appears when we do grouping for adjacent ones. We mentioned the maximum number of adjacent ones, we take it in a group, give more simplification for the function, which is our main objective. Our main objective when we solve for the function, the output function, f or y, whatever you call it, is to minimize this expression, because this means we use minimum gates, minimum number of gates in the design, and this save a lot of things, like money-wise, time-wise, many things. So when we have don't care min terms, this means this allow us to get more adjacent ones in one group. We mentioned before, we start with 8. We look when we, after we fill out the Karnaugh map, we look at 8 adjacent ones first to take it in one group. If not, we look at 4, then 2, and so on. So it's a good example we did last time, this one here, because without adjacent, without don't care, here don't care min terms in M0 and M2, we have to take only M1 and M3 as one group. So there's just 2 adjacent ones. But with using the advantage of these adjacent don't cares, which we can consider them ones in this case, so we can take the whole group as one group, like we have 4 adjacent ones now. So of course this gives a more simplification. Today we'll talk about combinational logic. Any question before we go ahead, please? Any questions? Okay. Please, everyone, interact with me, please. I need more participation. Yeah, I have people has good participation, but unfortunately, there are some others, fortunately few others, but didn't participate at all, or minimum participation. So please, I need everyone to participate. Just keep your attention with me, please. So we'll talk about combinational logic circuits today. We have 2 types of circuits in digital design or in digital circuit. Combinational logic circuits and sequential logic circuits. Today we'll talk about combinational logic circuits. Combinational circuits like have other, full other subtractor, comparators, multiplexers, demultiplexers, encoders, decoders. These examples of combinational circuits or combinational logic circuits. If we define combinational logic circuits, is the interconnection. Simply, it is interconnection of logic gates like and, or, all logic gates we discussed before. So interconnection of logic gates, the output is entirely function of the input. So the output is function of the inputs, entirely function of the inputs, which means we don't use clock pulses here. In combination logic circuits, we don't use clock pulses, which we use it in sequential circuits. So the main difference between combinational and sequential, as we will discuss later for sequential, in combinational we don't use clock pulses, but in sequential we use clock pulses. The output depends on the inputs beside the input clock pulse. But here it's just in combinational, it's just the outputs depends on the inputs only. So we mentioned examples like multiplexers, comparators, have others, but in sequential, as we will see, we'll talk about flip-flops, shift registers, counters. We'll talk about this. So in half other, as we mentioned before, for binary addition, not logic addition, binary addition, when we add x plus y, we get s. S stands for the sum, like refers to the sum, like the binary addition result. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0 with carry 1. And we put 0 when we write it down, like here, 0 with carry 1. So we can read 2 correctly because 1 plus 1 is 2. 1 in binary, equivalent to decimal 1. So 1 plus 1 in decimal is 2. In binary, 1 plus 1 is 0, and we have 1 here, is 0, 1. So we write it like this, 0, 1, but when we add it like this, we say 0 with carry 1. So simply the block diagram for half other, we have x and y are inputs, and the output is sum, associated with another output is carry out, C out, carry out. Because we mentioned when we have, like anyone here, 0 plus 0 is 0, the sum is 0 with carry 0. There is no carry here. 1 plus 0 is 1 with carry 0. 0 plus 1 is 1 with carry 0. But 1 plus 1 is 0 with carry 1. So as the sum output here, we have 0. As the carry out here, we have 1. So this means here, if we have 1 here and 1 here, so we have 0 here with carry 1 here. Okay. And this is the truth table, x and y. 0 plus 0 is sum is 0, carry out 0. 1 plus 0 is sum is 1, carry 0. 0 plus 1, sum is 1 and carry 0. 1 plus 1 is 0 with carry 1. We put sum here, not here in this column, to read it like this, 0 with carry 1. So we can read 2 here. Like in binary, this is 2 in this. 0, 1 in binary is equivalent to 2 in this. So the circuit or the logic diagram, logic diagrams means how the circuit represented in gates, logic gates. So this is called the logic diagram. So this is a circuit represent half other. So we have simply is exclusive OR connected with AND gate. So we mentioned 0 plus 1 is 1 with carry 0. So if we put 0 and 1 here as inputs, so exclusive OR function, similar inputs, 0 output. So we have different inputs here, 0, 1, so the output is 1. So the sum is 1. Same inputs goes to the AND gate, which is logic multiplication. So 0 times 1 is 0. So for 0 and 1 as inputs, the output sum is 1, and the carry out is 0. For 1, 1, similar inputs, 0 as the exclusive OR output. So we have 0 here. But as inputs to the AND gate 1 and 1, so the output 1 times 1, so is 1. So for 1, 1, as we see the function here, gives S equal to 0, and the carry is 1. So this is simply the circuit or the logic diagram of half adder. What is the difference between half adder and full adder? Half adder has only 2 inputs. Yeah, what's your code? What's it? 15? 1, 5? Okay, thank you. As we see here, the half adder has 2 inputs, only 2 inputs. But the full adder has 3 inputs. The full adder has 3 inputs. So what is the third input? The third input, if we look at the simple block diagram here, so we have the 2 inputs, X and Y, and Z. Z actually is carry in. The third input is carry in, come from previous stages or given. Like if this connected to the ground, for example, so carry in is 0. So either connected to the ground to represent the third input, carry in, or it comes from other previous stages, as we will see. Okay? So in this case, we have 3 inputs, X, Y, Z. So the truth table for this, of course, 2 to the power 3 is 8. So we have different unique combinations. So we have 0, 1, 0, 1, 0, 1, 0, 1. Then double the numbers as we mentioned, double zeros, double ones, double zeros, double ones. So we have 0, 0, 1, 1, and so on. Then again, double 0 for the next variable, next combination of the other variable. So double zeros, so 0, 0, 0, 0, double ones, 1, 1, 1, 1. So we got 8 unique combinations. No row similar to any other row. So let us add X plus Y, 0 plus 0 is 0, plus 0 is 0 as sum, and 0 as carry. 0 plus 0 is 0, plus 1 is 1 as a sum with 0 carry. 1 plus 0 is 1, plus 0 is 1 as sum, 0 carry. 1 plus 0 as inputs. 1 plus 0 is 1, plus 1 is 0 with carry 1. 0 with carry 1. 0 plus 1 is 1, plus 0 is 1 with carry 0. 0 plus 1 is 1, plus 1 is 0 with carry 1. 1 plus 1 is 0 with carry 1, so we put carry 1, and then in mind we have 0. So 0 plus 0 is 0. 1 plus 1 is 0 with carry 1. So we keep 0 in mind and we put carry 1 here. Then 0 in mind plus 1 is 1. So this is the outputs for these different inputs. Let us see this through this block diagram, how it works. So FA stands for full adder. So we have three others, full others, FA1, FA2, FA3, because the words we need to add has 3 bits. As we see word A, we need to add word A and word B. Each word A, we can see here 3 bits, word B 3 bits. So we need 3 full others to add them. So it's connected like this. We have 3 inputs we mentioned. So for the first full adder, we have inputs C0 is the carry input, and this is connected to the ground. Then we have two inputs, A and B. So we start with A0, the least significant bit, B0, A1, B1, A2, B2. So if we look at the word A is 1, 1, 0. So A0 is 1, A1 is 1, A2 is 0. Word B, excuse me, word B is 0, 1, 0. So B0 is 0, least significant bit. Please, we read from the first bit we read on the right and the last one on the left. So the first one on the right, we mentioned is called least significant bit, or LSB. The last one on the left is called MSB, or most significant bit. So B0 is 0, B1 is 1, and B2 is 0. So we put the inputs, and now we look at the output. Each output, or for each full adder, has two outputs, the sum and the carry. So the first one has S0 and C count, and so on, S1 and the carry, and S2 and so on, plus the carry. So again, we add the inputs first. So 1 plus 0 is 1, plus 0 is 1, with carry 0. So this carry 0, which is the output of full adder 1, goes to as the input, as carry in for the next full adder, and now with 0 value, with bit 0. Now we add 1 plus 1 is 0 with carry 1. So we keep 0 in mind and put carry 1 here. And this 0 in mind, we add it to the carry 0. So 0 plus 0 is 0. So the sum is 0. This carry out 1 is applied for full adder 3 as carry in. So we add A2 and B2. So 0 plus 0 is 0. Plus 1 is 1 with carry 0. So the outputs, we look at S0, S1, S2. So what is the output? Is 1, 0, 1. What is the result of the addition, which is our output here? Is 1, 0, 1. Let us check analytically with our traditional addition, binary addition. We have the two words 1, 1, 0. The other one is 0, 1, 0. We add them up. 1 plus 0 is 1. 1 plus 1 is 0 with carry 1. We put carry 1 here. Then 0 plus 0 is 0 plus carry 1 is 1. So 1, 1, 0 is equivalent to 3. Represent decimal number 3. 0, 1, 0 represent 2. If we add 3 plus 2 is 5, which 1, 0, 1 is 5. In binary, 1, 0, 1 is 5 in decimal. So we are okay. Please, this example we should know very well. And please tell me if you have any question here so far. Any question here, please? Okay. So if we look at the logic diagram for full adder, it's actually is two adders, is a connection, two half adders, is a connection, mainly is a connection of two half adders, as we see. We mentioned the half adder, the log diagram of the half adder is a connection of exclusive OR and AND gate. So we have exclusive OR and gate, another exclusive OR and AND gate, and combined together through OR gate. The last gate is OR gate to get the carry out here. So it does the same function we mentioned. So, for example, if the two inputs 0 and 1 with carry 0, 1, so 0 and 1 as inputs goes to the first, the exclusive OR here, the first one. So different inputs, so we got 1 as the output. And the same inputs goes to the AND gate, so 0, 1 multiplication, so it's 0. So we have 1 and 0 here. So this one applied to the second exclusive OR. And we have carry in the other input of this exclusive OR came from carry in. So C0 is 1. So again, different inputs. 0, 1. Sorry, we talk about 1 here. We mentioned the inputs are 0 and 1. So the output of the exclusive OR, we talk about the black writing here. So it is 1 and 1. 1, we take this one and 1. This red one came from the carry in, C0. This black one here came from the two inputs 0 and 1. So we have 1 and 1, which is the output is 0. We talk about the black one. So the sum is 0. And at the same time, this one applied for the AND gate, this black one. And we have another one came from the carry in. So the output will be 1. And we have this 0 and 1, as we mentioned, at the same time applied to the AND gate, so the output is 0. This 0 goes to the second input for the exclusive OR. So we have 1 plus 0, so it gives 1. So the output is sum 0 and the carry 1. So if we look at 0, 1, 0x A0, like XYZ. So like 0, 1, 1, 0, 1, 1 here. In the truth table, we have sum 0 with carry 1. Sum 0 with carry 1. If you look at 1, 1, in the red one, so we have 1 and 1, A0 is 1, B0 is 1, and C0 is 1. So we talk about the red color now. The bits in the red color. So 1, 1 for the exclusive OR gives 0. 1, 1 for the AND gate gives 1. We talk about the red ones. And we have a red one from the carry. So we have 0 and 1. We have 0 and 1 for the first exclusive, for this exclusive OR in the last stage. So we have 1. Different inputs, so we have 1 as the output. Then we have 0 and 1 for AND gate multiplied, so 0. With carry 1, the other input for the OR came from the output of the AND gate. So 0, 1 is exclusive OR, so logic addition, it is 1. So 1, 1, 1, it gives 1 as the sum and 1 and the carry 1. 1, 1, 1 gives 1 and 1. Okay. Just to follow step by step for the inputs and the outputs, you can get the whole outputs as listed in this truth table based on these different tables. Like we did here, 2 examples to see how it works. Any question here, please? If you have question, please let me know. Any question? But
Professor?
question?
Professor, I have a question.
Yes,
hear me?
speak louder, please. Your voice is very,
Can you hear me?
yeah. Okay.
I was wondering if when we do the simulations, are we gonna have the full adder? Like, is it gonna be one block in the simulator, or are we gonna have to
Can
like
you
manually?
speak out? Your voice is away. I don't hear you. Okay.
I can turn it up louder. I don't want to turn it up too loud.
Is it
Yeah,
better?
just speak louder a little bit, please. Bang, is it bang?
Yeah.
Yeah, bang. Just speak louder, please. I heard you talk about simulation, but I don't know exactly.
I'll type it in the chat.
Okay. In simulation, we can use both. We can use if I heard you well, the simulation you say how we represent this in simulation is
Yes, yes.
yeah, we
I
have
wanted.
go ahead.
Can you hear me now? Max volume.
Yeah, I still, yeah, again, in simulation, we can use the gates. Okay. We can create the circuit in gates. Okay. If I hear you right. This is this a slide or this one? This one or this one? Okay, okay, Bang, let us talk at either in the break or at the end of the class because I don't hear you. Okay, so let us chat at the end. Control the inverter. A component based on this is called control the inverter. What is this control the inverter? As you see, exclusive ORs with two inputs. One input is called invert, and the other inputs for the data. So this like gives negative numbers because we invert, like we use one's complement here. So we invert the inputs. We can invert the inputs or we can keep it as it is. So for example, here is for these inputs, you see here connected to the inverter or the invert input. The invert input, if it is one, and assume this input A8, assume A8 is 0. So what we get at the output Y8?
1.
We get 1. Perfect. What's your code, sir?
2.
2. Okay, thank you. So this means when we insert here bit 1 as invert, as the invert input, I mean, so this inverted the input. Because if it is 0, we will get 1. If it is 1, so we have 1, 1 as inputs, similar inputs. So we get 0 at the out. So connecting this input, which is common for all these inputs here, one input of all gates, invert the data. So like we got one's complement, which represent a negative number. If this input is 0, so this means not invert. Because if we have 0 here, A8, so 0, 0, similar inputs, 0 out. So it doesn't invert A8. It keeps it the same as the out. If it is 1, so we have 1, 0, so we have 1 as the out. the same input. So to invert, we connect this input, invert input to bit 1. For non-invert, we connect this input to 0. This actually it's just a portion of a circuit. Is called other subtractor. A circuit, we use it for other and subtractor of binary numbers. So this circuit we see here is other subtractor. So it has controlled inverter here connected to full others. Connected to full others. So how it works? This circuit either add or subtract binary numbers. So if we have two words or two numbers, two binary numbers, A0, A1, A2, A3, and the other binary number or the other word, we call it word also, is B0, B1, B2, B3. So assume A0, A1 or word A is 1011, 1011, like it's given here, 1011. Again, for the first one here, this for A0. The last one on the left, this for A3. So 1011. For word B, 0100. So 0100. And we need to add, one time we need to add these words or these numbers, A and B. And another example, we need to subtract A minus B. So let us see how it works. First of all, let us take the example for subtractor verse to work as subtractor. We mentioned this M, it means the mode. M stands for the mode, which equivalent to the invert input here. So if this M or invert, let me just confirm here that this M is invert. M. So if M is 1, and you see M is applied here, 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 and here. It's not connected here. It's not connected for this. You see there is no node here. The node here means we have connection, we have soldering at this point. But when we have two lines like this, okay, let me. So usually when we draw circuits, say if we have two wires here and we have connection here, so we put node here. Means we have soldering here. So there is a connection here. But when we have something like this, without a node here, so this means at this point, there is no connection. No connection. This is a terminology used in when we draw circuits. If we have a node, we have connection. If there is no node, like two wires, just yeah, the projection looks like connected, but they are not. But for connection, they already connected. Okay. So M is connected to this point, this point, this point, this point, and this point here. Okay, so this means we have one here, we have one here, we have one here, and we have one here. When we have one, so one of the inputs of the exclusive force are ones. So 1, 0 is 1 here. We talk about the highlighted inputs and outputs now. So 1, 0 means we have 1 here. 1, 1, we have 0 here. 1, 0, we have 1 here. 1, 0, we have 1 here. So this is the outputs of the exclusive ORs, which represent inputs for the full adder. What is the other input of the full adder? It came from word A, 0. Or word A, 0, A1, A2, and so on. It's given A0 is 1, so we have 1 here. A1 is 0, so 0 here. A2 is 1, so 1 here. Goes to the full adder, and the last A3 is 1, is applied for the full adder. Now, as we see here, each full adder has 3 inputs. One came from A, and the other one came, the other bit come from the output of the exclusive force. Okay, so now we add, like we add binary numbers. Yeah, we subtract, but actually we subtract, but as process we add here because we use full adder. So there is carry 0 connected to the full adder came from the M also, or the invert input, so we have 1 here. So let us proceed. 1 plus 1 is 0 with carry 1, so we put carry 1 here. And we keep 0 in mind. So 0 plus 1 is 1. Next one, 0 plus 0 is 0 with 1. So it is 1 with carry 0. Then 1 plus 1 is 0 with carry 1. So we keep 0 in mind and we put carry 1 here. So 0 plus 0 is 0. The last one, 1 plus 1 is 0 with carry 1. So we put carry 1 here. And we kept in mind the 0. So 0 plus 1 is 1. So this is the output of subtraction. 1, 1, 0, 1 in this order. Start from S0, LSB, and end with S3, which MSB. Of course, we ignore these carry 1s as output. So when we subtract A minus B, because we inverted B input, so this means minus B. So A minus B, we got 1, 1, 0, 1. Let us check analytically. We have 1, 0, 1, 1, and 0, 1, 0, 0, like traditional subtraction of binary numbers. So 1 minus 0 is 1. 0 minus 1 doesn't work, so we have to borrow 1 from the left side. This one, we put it beside the 0, not overlap 0, beside the 0. So 0, 1 minus 1, like 2 minus 1 is 1. Then this one is already gone to the adjacent bit, so we have 0 now. 0 minus 0 is 0, 1 minus 0 is 1. So we got 1, 1, 0. 1, 0, 1, 1, 1, 0, 1, 1, equivalent to 13, or represent 13 in decimal. 0, 1, 0, 0 represent 2. 13 minus 2 is 11. If we check 1, 1, 0, 1, it is 11. If we put the weights, we have 1 and 2 here, 4, 8. So 8 plus 2 plus 1 is 11. So we are okay with this subtraction. For addition, if we need to add A plus B, so now we put or apply 0 bit at M. 0 bit doesn't change the other M. Like it doesn't change the B word. So when we put 0 here, now we talk about these other inputs for the full adder. So 0 gives 0. 1 gives 1, no change for the input. Because we just add here, so we don't change anything. 0 gives 0, 0 gives 0. Of course, word is the same. And of course, here the carry, the new carry here is 0. So 1 plus 0 is 1, plus 0 is 1, with carry 0. 0 plus 1, 0, this 0 plus this 1 is 1. Plus 0 is 1 with carry 0. 1 plus 0 is 1, plus 0 is 1 here, with carry 0. And then 1 plus 0 is 1, plus 0 is 1, plus carry 0. So what we got here, for addition, we got 1, 1, 1, 1. So A plus B is 1, 1, 1. The check, like using regular or traditional subtraction, 1, 0, 1, 1, plus 0, 1, 0, 0, so it's 1, 1, 1. So 13 plus 2 is 15, so 1, 1, 1, 1 actually represent 15. Any question here? Any question?
Professor,
Yeah, go ahead.
do we need to draw this out or like write the numbers down or do questions like this on the exam?
What is that again?
Do we need to do this on the exam?
I'm not talking about the exam here. I'm talking about, do we see this part? Do we understand this or not? Exam this is another story, okay? But is the function here is not clear? Please tell me, I can go back and explain whatever you miss.
Do you
Guys,
mind?
the exam is a tool, is not objective, is not goal. The exam is not goal. The exam just a tool to like pay more attention, and because we have exams, so we have to take care about our stuff. So it is a tool, not objective. The objective to understand the material. Okay? Yes, sir. Go ahead.
Do you mind explaining again the carry another? The for another?
Okay, sure. Okay, let us talk about subtraction, because addition is easy. So we subtract A minus B, okay? So to subtract A minus B, this circuit designed to do this subtraction. So we apply bit 1 at M. Why we apply bit 1? Because we mentioned one of the negative numbers, one of the approaches to get negative number, we mentioned either we use sign magnitude, or 1's complement, or 2's complement. So because 1's complement is easier in the circuit, so we use here 1's complement. 1's complement, if you remember, we just invert each bit in the positive number to get the negative correspond. So we need A minus B. So we need to invert B word or B number. So we applied 1 here, such that the 2 inputs goes to this exclusive OR. So when we have 1 here and the input B0 is 0, it will be inverted to 1. Because we mentioned the function of the exclusive OR is similar input, 0 out. If the 2 inputs are different, the output will be 1. 1 applied here, so invert this 1 to 0. 1 applied here, so invert this 0 to 1. 1 applied here, so invert this 0 to 1. So these are now are the outputs of these exclusive OR, which are one of the inputs of the full adder. The other input for the full adder came directly from the A word. So we have 1, 0, 1, 1. Now, just we do the same thing we did here. Now, because we have now, we prepared the inputs for the full adders here. Do you remember when we mentioned before, if we need to subtract the two numbers? So, generally speaking, addition is easier than subtraction. So we use the advantage of 2's complement to convert the negative number to 2's complement. So 2's complement number is actually a number, but represent a negative value. So we just add the other number with this 2 complement representation. So we add them up, but actually we subtracted them. So this is the same. Now we convert B from positive to negative. Then we add this negative number with the A word, so we get the result of subtract. So again, we have C0 verse here is 1.
I still have a question.
Let me just
No, the same question. Yeah.
complete the answer for, and I will get back to you, okay? So 1 plus 1, we mentioned 1 plus 1 is 0 with carry 1. So we put 1 plus 1 is 0 with carry 1. So we keep 0 in mind and put carry 1 before we forget. So we put carry 1 here. And we have in mind the 0 because we still have another input we didn't add it yet. So this 0 plus 0 is plus 1 here. So it is 1. So the sum is 1 with carry 1. Next one, 0 plus 0 is 0, plus 1 is 1 with carry 0, of course, because we don't have carry. 1 plus 1 is 0 with carry 1, so we keep 0 in mind and put carry 1 here before we forget. Then we go back 0 plus 0, here is 0. Then 1 plus 1 is 0 with carry 1, so we put carry 1 here. And we have 0 in mind, we add it to this one, so we have 1. Like we do normally when we add, like 1 plus 1 is 0 with carry 1. We put 0 with carry 1, and so on. So we got 1, 1, 0, 1. So this for subtraction. For addition is simpler than this. It's just you just add the numbers. Yes, sir. Go ahead.
Yeah,
Yeah.
you talked about how we invert B into 2's complement form
Yeah.
for subtraction. I was wondering, why do you invert the first 0 bit? Because I remember you mentioned to us that for 2's complement form, we start
Yeah, we
inverting
use
numbers.
here, as I mentioned this actually, we use here 1's complement. 1's complement is another form of the negative numbers.
Okay, 1's complement.
It's not wrong. It's not wrong. It's another form. But we mentioned the actual number stored in the computers, the negative number stored in 2's complement. But we have different approaches here. So we do a circuit here. And actually this other subtractor circuit is designed on this base. Like you use just 1 complement to do the function which we need here.
Okay, I see.
For
Thank you.
For this circuit.
For
For
this
the
circuit.
purpose of the design of this circuit. Okay?
Okay.
Any other questions, please? Okay. Comparators. Okay. To compare, I hope we get a chance to do a lab using this, hoping. So we'll see. Comparators, to compare the magnitude of 2 binary quantities to determine the relationship of these inputs or quantities. So the comparator is here. We have two different words as inputs, input A and input B. So we have A0, A1, A2, A3, B0, B1, B2, B3. And as the output, we have three different outputs, A greater than B. When we compare A and B, either we have A greater than B, or A equal B, or A less than B. So based on the result of comparison, so the correct answer will be on, like bit 1. So for measurement, if for example A greater than B, so the output of A greater than B will be on and the rest will be off. If A equal B, so the A equal B output is on and the rest are off. Similarly, A less than B. So if A is less than B, so A less than B is on and the rest will be off. So as an example for this, if word A is 0011, which represents 12, and B is 1001, which represents 9. So what do you think? Which output here will be on or logic high? Which one of these for these two words or two numbers?
First
First
one.
First one, perfect. Because A is 12, B is 9, so definitely A is greater than B. So the output A greater than B will be on or logic high, and the rest will be logic low. What's your code, sir?
7.
So, same people, guys. Thank you, Chin. Thank you. We need new people, please. Okay. This actually is very important component. Is used in different applications. Used in there is ICs called 555, 3555 or timer. We use it inside this IC to compare between different levels. So it has many applications. Also in digital signal processing, we use this. So it's good to know what is the function of this component. Multiplexer, we discussed the multiplexer before when we did the lab. It's called also data selectors because we mentioned multiplexer has many inputs or different inputs, and based on the control inputs or selected control inputs, S0 and S1, we pick up one of these data inputs, either D0 or D1 or D2 or D3, which appear at the output. So only one input out of the multiple inputs will appear at the output based on the choice of S0 and S1. And I show you a simple example for how we use this multiplexer as a key encryption to encrypt the function of exclusive OR gate. So the keys was S0 and S1. So S0 and S1, S stands for select or control input, or key, the key for the encryption when we use it to encrypt other gates. So 4-to-1, this is a 4-to-1 multiplexer, means we have 4 inputs, D0, D1, D2, D3, and 4 is equal to 2 to the power 2, so we have two S0, 2 inputs, 2 control inputs, S0 and S1. So this actually the logic diagram for this multiplexer. We can see here when we choose the name, it's careful. We choose carefully the names. Logic diagram. Why we call it logic diagram? Because we have here just gates. But if we say circuit diagram, so this means we have to put the circuits inside each component here. We must draw like the inverter here. What is the circuit inside the inverter? Like I give you a quick example. We have transistor, we have resistor, we have ground. So this is not circuit diagram. It's called the logic diagram. So like higher level above the circuit, because circuit goes deeply inside the IC or inside these gates, which is not necessarily here. Here is because we talk about digital, so we mainly focus on inputs and outputs. Inputs and outs. So we don't have to go deeply through the circuit inside. We just give example for how it works as a circuit, but yeah, we focus on logic diagram. So we have S0 and S1 connected to inverters here, and this IC is number 7404, and the inputs are connected to AND gates with IC number 7411, and the outputs are connected to OR gates with number 7432. As we see here, all technology used is TTL, not CMOS. Why TTL? Because the number of ICs start with 74. We mentioned for CMOS, start with C, most likely. And why we use CTL? Because we mentioned this is faster operation. Power consumption here isn't too much. So we don't care about it. We care about fasting the process. We need inputs. We need to get the output as soon as we can. So for this example, we have the input data D0, D1, D0, D1, D2, D3 given, and S0 is 1 and S1 is 0. So what is the output? S0 is 1 and S1 is 0, so means 1, 0, this corresponding to input D1 or decimal number 1, but we talk about inputs D0, D1, D2, D3, so this represents D1. D1 is 1, so this means the output, which equal to D1 based on these control inputs. So the output will be 1. If S is 0 and S1 is 1, so this means we talk about the D2, input D2. D2 here is 0, so this means Y equal to 0. If we follow these inputs on these gates, like again, D0, D1, D2, D3, and S0 is S0 is 1 and S1 is 0. S0 is 1 and S1 is 0. So if we look at here, S0 is 1. So the output of this inverter is 0. So this output of this inverter goes as one input for this gate. So immediately the output of this gate is 0. Because this is AND gate, logic multiplication. So regardless of the other inputs, since multiplied by 0, it will be 0. So this gate is 0. And also this gate will be 0. Okay. And this one here goes to this circuit. So we have one input here. One input is 1. And also we have 1 also here. No, we have 0. Oh, okay, we have 0. S1 is 0, so invert it to 1 here also. So we have 1, 1. So keep this gate now, because we have 2 inputs are 1s. Let us look at this gate. This gate, we have 0, so the output will be 0. And S1 is 0, right? S1 is 0. So we have 1, 0 here. So the output of this gate is 0. The output of this gate is 0. So we have 0 here. The output of this gate is 0. Okay, so we have 0 here. Now this gate here, we have 2 inputs has 1s. So the output of this gate will depend on the data input. The data input is D1. So what is D1? D1 is 1. Okay, so this means this input, this is the only input, this is the only gate, has 3 1s as the input. So the output will be 1. So 1 plus 0 here, we have 0 and 1, so we have 1 here. So we have 1 here, we have 0 here, inputs for this OR gate, so Y will be 1. So in this case, Y will be 1. If we follow the inputs as in and out of these gates. Similarly, for other inputs, the same thing. You will see like 3 of the gates will be out. I mean, the output will be 0, and 1 only has output 1 based on the 3 inputs. And again, this is the truth table. A demultiplexer, okay, let us take like 5 minutes break, please. Or 10 minutes, okay. 10 minutes is okay. So 3:50 now, 4 at 4, we will continue this this part, okay? So 10 minutes break, please, okay? Okay, welcome back, everyone. Okay, now we'll talk about any question, please, before we go ahead. Any questions here or before that, whatever? Any question, please? Okay. So for multiplexer, we mentioned we have multiple input and one output. So what do you think for the demultiplexer? In demultiplexer, we have one input and multiple outputs. So this single input appears at one of the outputs. Before, we have multiple inputs and one output. So based on S0 and S1, or control inputs, because it may be more than S0 and S1, maybe S2, S3, if we have more inputs, based on the type of multiplexer. So based on the control inputs, one of the data inputs is selected to appear at the output. But in demultiplexer, as we see here, we have one input and multiple outputs. So based on S0 and S1, which we have it here, so this input appears at one of these outputs. So if we look at the truth table here, so if S0 and S1 both of them zeros, so this means we talk about D0. So if the input is 0, D0 will be 0. If the input is 1, D0 will be 1. So this input appears at D0. This input appears at D0. So if the input is 0, D0 will be 0. Of course, the rest will be zeros. If the input is 1, D0 is 1, and the rest are zeros. If we have S0 is 1 and S1 is 0, so we talk about D1. So if the input is 0, D1 is 0. If the input is 1, D1 is 1. 0, 1 means we talk about D2. So if the input is 0, D2 will be 0. If the input is 1, D2 is 1. 1, 1, S0 is 1 and S1 is 1, so we talk about D3. So if the input is 0, D3 will be 0. If the input is 1, D3 will be 1. This is simply the function of the demultiplexer. Decoder is a circuit, has only control input, no data input. So the controller, the inputs are only data control input. There is no data inputs here. So this is simply the logic diagram for decoder. So if we look at the truth table here, for example, say we have A0 is 0, A1 is 0, E inverted is 0. So 0, 0, 0. So this E inverted is 0. So the output of the inverter will be 1. So 1 will be applied to all these gates. Let us look at the other input. A1 is 0. So this gate has input 0, and this is NAND gate. So input 0 means whatever the other inputs are is multiplication, so the output will be 0. And we have inverter here because this is NAND gate, so this invert 0 to 1. So D3 will be 1. Also, we have 0 here input, so D2 will be 1. Also, we have 0 input here, so D1 will be 1. D1 inverted, I mean, this output will be 1. Now look at D0. We mentioned we have 1 here. Then the other input came from the inverter, which is 1. And the third input came from the inverter, so we have 1, 1, 1. 1, 1, 1 for AND gate, it will be 1, but this NAND gate means the output is inverted, so D0 inverted will be 0. So for 0, 0, 0, 0, which if A0 is 0 and A1 is 1, and A1 is 0, so we talk about D0. So D0 is 0, D0 inverted because the outputs here are inverted. This is easier for the design for this case. So the only output is 0 is D0 inverted, and the rest are 1s. For A0 is 1 and A1 is 0, so this like represent D1 or D1 inverted here. So what do you think? Only D1 inverted will be 0 and the rest will be 1s by the same approach we did, the same sequence. So you can get D1 is 0, I mean D1 inverted is 0 and the rest are 1s. 0, 1 means D2, so D2 inverted is 0 and the rest are 1s. 1, 1 means D3, so D3 is 0 and the rest are 1s. If E inverted is 1, what is the symbol here under A1 and A0?
It does not matter.
What is that?
Does not matter.
Which mean what we call it exactly? We call it don't care. Yeah, this you are right, but we call it don't care. What's the code say?
2.
2. Thank you. Don't care means whatever A0 and A1, don't care if we have E inverted is 1. Actually, E inverted or E stands for enable input. Enable input. Like control input to control the function or the operation of this circuit. So if E inverted is 1, so what happens? We have 0 here. We have 0 here. We have 0 here. And we have 0 here. So all outputs will be 1s. Example of the decoder is very important example or very important application is the BCD to 7 segment decoder. And the IC number is 7447. This decoder, we use it to convert from binary number. Remember, this is decoder. So we convert from binary to decimal. But encoder convert from decimal to binary because we encode decimal number to binary. But for decoder, we use it actually when we have digital inputs or binary inputs and we need the corresponding decimal numbers in circuits. In circuits, not calculations. Encoder is a digital circuit that performs the inverse operation of a decoder. So it's actually encode decimal numbers to binary numbers. Any questions here, please? Any questions? Any questions? Okay, since we still have time, so please let us talk a little bit about sequential circuits or sequential logic circuits. Um, so the previous part we spoke about combinational logic circuits in general, combination. Yeah, we talk about the gates, but inside the gate circuits. But when we draw the diagram, we talk about logic diagram because we talk about the gates. But in general, we mentioned combination before means the output depends on inputs only, like we saw. We don't use clock pulses. In sequential logic circuits, we depends on, or the output depends on the inputs and also on the input pulses. So, like we'll talk about latches, we'll talk about flip-flops, and these are the basic building blocks for shift registers, counters, memories. So the output depend on the input and clock pulses. The building blocks of sequential circuits are latches and flip-flop. Examples for this, like shift registers and counters. So latch, what is the latch? The latch is a memory element. It stores one bit, either bit 0 or bit 1, as we will see. You have only one bit stored per each latch. Latches, there is no edge trigger. Flip-flops, we use edge trigger. Latch and the flip-flops are memory elements. But as we will see, for latches, we don't use edge trigger. But in flip-flops, we use edge trigger. The commonly used latches, basic SR latch, gated SR latch, gated D latch. For the basic SR latch, okay. So this is the logic diagram for a latch. There are different versions, as we see here and also here. So all of them do the same function, but just different gates. So let us look at the basic one here. So as we can see here, we have two NOR gates connected in this way, and this gives us the function of a latch as memory element. So what is the truth table for this latch? We have two inputs here, S and R. S and R. Simply S stands for set. R stands for reset. So for the inputs, S is 1 and R is 0. Please, if you follow me and focus with me, it will be easy, believe me, easy to understand, okay? So please don't be busy with something else. If S is 1 and R is 0, means set the output to 1. The function of the latch gives the 1 as the output. So if S is 1 and R is 0, it simply sets the output to 1. If R is 1, bit 1, and S is 0, simply reset the output to 0. If both of them are zeros, R 0 and S is 0, so no change at the output. The new status will be the same as the previous status of the output. If 1, 1, if S is 1 and R is 1, this is not allowed. It's not allowed to, for S and R, the two inputs of the latch, to be ones at the same time. So in any design, we have to be very careful, such that we never allow in the circuit for R and S to be ones at the same time. Why? Because we don't know the output. The output cannot be predicted if R is 1 and S is 1 at the same time. How? We'll see we will see how this happen in the circuit or in the logic diagram. So even if you don't have the truth table, so you can remember the truth table in this way. S is 1, R is 0, means set the output to 1. If R is 1 and S is 0, means reset the output to 0. 0, 0, no change. 1, 1, not allowed. The output here is Q. The output is Q. But usually, we take another, like another output, but it's still the same. Q inverted. So if Q is 0, Q inverted will be 1. If Q is 1, Q inverted will be 0. So actually we have one output Q. This is when we talk about the output, we talk about Q, not Q inverted. But because by default, Q inverted will be the invert of Q. And just like more advantage to get another option if you need Q or Q inverted. But the output we talk about here is Q. To differentiate between the new status and the previous status, we talk about Qn plus 1 and the Qn. So Qn plus 1 means the new status or the new output. Qn means the previous output. So when we say Qn plus 1 for S is 0 and R is 0, when we say Qn plus 1 is Qn, this means there is no change in the new output. Okay, let us now see how this circuit works, or this connection works for inputs if S is 1 and R is 0. If S is 1 and R is 0, and assuming the initial state or given the initial state is 0, is the initial output state is 0. Initial Q is 0. So if Q is 0 as initial, Q inverted will be 1, of course. Okay. So these are NOR gates. So it's simply the function of the OR and then invert the out. So if S is 1 here, S is 1 applied at S bit 1. And the initial output is 0. So we have 1 and 0. So what is the output? For OR is 1. Logic addition. Then invert it to 0. So the new output here is 0. The new Q inverted is 0. This 0 is applied to the second NOR gate here with another input R is 0. So 0 and 0 is 0 inverted to 1. So the new, we talk about the red ones here, okay? The red bits without circle. The red bits like 0 and 1. So the output now Q is 1, and of course Q inverted is 0. So this satisfies the first row here. S is 1, R is 0, the output is 1. The new output is 1. So S is 1, R is 0 as we look at the function here. So Q, the new Q is 1, or Qn plus 1 is 1, because Qn is 0, the initial status, and the Q inverted is 0. As this example, you can do the same thing for the rest of the other inputs. Starting from S is 1 here, and then follow for the rest of the function. Now, let us see what happens. Okay, let us take another example, like 1 and 0, okay? So, just to confirm. So, we assume S is 0 and R is 1, like the black bits in circuits. So S is 0 and R is 1. Again, S is 0. Initial state is 0. Initial state is 0. So Q is 0 and the Q inverted is 1. So S is 0 here. And we have initial state is 0. So 0 plus 0 is 0 inverted to 1. So we have 1 here inside a circle. Just to differentiate with other bits. So this one applied to the other NOR gate with another 1 here. So 1 and 1 is 1 inverted to 0. So the output is 0. So we can see here, this represents the second row in this truth table. If S is 0 and R is 1, reset the output to 0. So we reset the output Q to 0. And of course, Q inverted will be 1. And so on. Now let us look at if we have 0, 0. I mean, if we have, by the way, if we have 0, 0 at the inputs, so the new output will be 0. This means the new output is 0 and the initial state is 0. So this means there is no change. So 0, 0, no change. Now let us look at 1, 1. What happens at 1, 1? We mentioned this not allowed. Why? Because we cannot predict the output. Imagine you put the design in certain stage, which like the output here must be 1 to get in the next stage to get 0 or whatever, to get at the end the correct function of the system. Imagine in certain phase in the design, you have component, you don't know what is the output. It's disaster, right? So this is not allowed. Why not allowed? Okay, let us see. So assume we have 1, 1 here. The red ones in circles. Again, applied. So at S is 1. And its initial states are 0. Initial states, so Q is 0 here. So we have 1 and 0. So is 1 inverted to 0. So we have 0 in circle here. This 0 goes to the other gate with 1 on the R input. So 0 and 1 is 1 inverted to 0. So we have another 0 here. Imagine now, you have Q is 0 and the Q inverted is 0. This has never happened because we know by default, if Q is 0, Q inverted is 1. If Q is 1, Q inverted is 0. but never ever be the same, both of them. So this means what? This means we can't predict the out. In it can be 0, 0 or 1, 1. In the lab, when you do simulation, sometimes it gives you 1, 1, and sometimes it gives 0, 0. So, but for this analysis here, we get 0, 0. Okay. So that's just to prove for, yeah, and this 1 and 1 is not allowed at all to be at the input at the same time, because 0, 0 means we don't know the output, because this is not correct output. We don't know the output. Everyone sees this? Any questions?
Yes. No.
Okay, good. These are other versions of the latch. We can use NAND gates, but in this case, the inputs will be S inverted and R inverted. S inverted and R inverted is simply say if S inverted is 1 and R inverted is 1. So exactly like you do here, for S is 0 and R is 0. So this is no change. So like if S inverted, R inverted are ones, exactly we talk about S and R zeros, so this means no change. If S inverted is 1, inverted is 1, and R inverted is 0, so we talk about S 0 and R is 1. So reset the output to 0, like this one here. So this is called active low, because we talk about inputs S inverted and R inverted, but the original one we talk about active high, because we talk about S and R, not S inverted and R inverted. Another equivalence here, this is the last thing we'll talk about today. So just 1 minute, please. Okay, and let me rotate this. Okay. Another version here, like negative OR. This is another design of a latch using negative OR. The same thing. S inverted and R inverted are inputs here. So if S is 0, S inverted is 0, and R inverted is 1. So like we talk about S is 1 and R is 0. So this is the output to 1. And of course, for Q inverted will be 0. Negative OR, we spoke about the negative OR before. What is the output of the negative OR? We mentioned OR gate is A plus B. Negative OR, it gives A inverted plus B inverted. This is exactly equivalent to NAND gate. Why? For NAND gate, we have two inputs A and B. Multiply, so AB invert, because this NAND, so is AB inverted. AB inverted based in De Morgan's theorem, cut this bar here in the middle and switch the operator here, so is A inverted plus B inverted, which equivalent to negative O. So this exactly equivalent to this circuit. When we use inputs is inverted and are inverted. Different designs for different purposes, okay? But this is the original one. And we, so mainly we explained this one, and this is very similar for this one. Okay? Take one example here. Assume we have S inverted is 0 and R inverted is 1. So the same thing. S inverted 0 and the initial set is 0, 1. So take 1 and 0, multiply, so it is 0, so inverted to 1. This one was 1. So multiply is 1 inverted to 0. So we got 0 here. So exactly like S is 1 and the R is 0, so set the output to 1. Okay. So the same functions but different gates for different design. Next time we'll continue with this part. So any question here, please? So far. Any question?
The midterm next class, is that going
Yeah,
to be like
midterm
during,
next class
That's
up to the end of note 6. Today is not included.
okay,
What we discussed today is not included in the midterm. Okay?
okay.
Will the midterm be similar to the quiz?
What is that?
Will the midterm be similar to the quiz?
Yeah, similar to the quiz, similar to the homework. Yeah. And based on our discussions here. So please review the notes carefully, so it will be fine.
Professor, will the midterm also include material from the first few weeks of class, like the quiz?
What is that?
Will the midterm include material from the first few weeks of class, like the
Yeah,
quiz?
from the beginning up to end of note 6.
Okay, thank you.
Any other questions? Okay, thank you, everyone. Have a good day. Have a good weekend.
Thank you,
So-
Professor.
Have a good
Yeah.
weekend.
You too. Take care. Bye.